it looks like what you've done so far is really good. Like there's learning happening, there are light bulbs glowing, like really we can't ask for a whole lot more than that. But I do want to just clarify a couple of pieces to put the good physics in there with the experimentation that you are doing. Does that make sense? So the first thing is, on that first question, it asks you to diagram the circuit, right? And I see lots of really cool pictures. I see lots of like kind of artsy pictures and things like that. And that's great, except that there are very specific ways to draw what they call a circuit diagram. And I want you to know those so that if you are taking a class in college or you're doing something someday where you need to draw a circuit diagram, people know what you're talking about and they don't laugh at you. Because I don't want them to laugh at you. I want you to know like the lingo for it. Does that make sense? You'll also need to know this when you're working on your homework because there are pictures like this in your homework too. So you can write this down on your notes. You can write this down on your lab. You can write this down on your blue sheet. Whatever makes sense to you. I just wanted to share a couple things, like I said, to make sure that it's that we're all doing the same deal. So just circuit diagram basics. So what's one thing that you have in your circuit? One thing that you had to draw a picture of?
A battery.
A battery, right? So we take a battery, we look at it, it looks something like this. Maybe if you're artistic, then you make it look more like a cylinder, but something like that, right? Again, we know that the bumpy end is the positive and the flat end is the negative. And that's all well and good, but that's not really how we draw it in a circuit diagram. A circuit diagram, a battery is going to look like this. It's going to be a long line and a short line. And then we draw wires coming out of it. They come out either side. So that is a battery. Okay, the long side is the positive side, and the short side is the negative side. Often when I draw circuit diagrams, I put the plus and minus there just to remind myself and to help students so that they know. But it's not, you don't have to have the plus and minus there because that's why you have the long and short side, right? It's so that you can indicate what's going on there. In the last question that you have from the lab, it asks you to double the voltage. So doubling the voltage is what you have to do when you have a flashlight, like one of those handheld flashlights, right? How many batteries go in a flashlight? Two, right? And you stack them up, and then you just hold them there, and that's how they work. And there's one end, there's an electrode at the bottom, there's an electrode at the top, and in the middle they're just touching, right? So you've just got the bumpy end and the flat end right next to each other, and then your light bulb or your flashlight lights up, and it's exciting. That's exactly what we're doing when we're doubling the voltage. We're just going to stack the stack the batteries up. So when you hook that up, you can't literally stack your batteries, but you can connect the positive of one battery to the negative of another battery. Does that make sense? So you would put a little wire in there when you're actually doing it, but when you show that you have multiple batteries or multiple what they call cells in a circuit, you'll draw it like this. So a long, short, long, short. So that looks like it would be a stack of two batteries, but it actually is how we would draw any stack of batteries. So even if you have four batteries, right? Like if you have like a little remote control car and you have four batteries in it, you still would draw the circuit with just, you don't have to like draw like a huge stack that goes on forever because that just is kind of silly. So this is a single cell, and then this is actually a battery or a set of cells. Life's good? Okay, that's one thing in your circuit. What else do you have in your circuit? What else do you have? Take a look at it. Well, what you got?
A light bulb.
You have a light bulb, right? Absolutely. So we have a light bulb, so we might draw a light bulb. Oh, it's so cute. And then it's got that filament in there, something like that. And that's a pretty nice, well, not perfect, but it's a pretty nice picture if I do say so myself. But again, that's not what the circuit diagram folks, what makes sense to them. A light bulb in a circuit diagram, it's going to have your wire coming in and out, and then it's a circle with a loop-the-loop wire, or it's a circle. Sometimes they put like a jagged wire in there. Okay? Either way, you can kind of see the resemblance, right? Okay, so you've got the glass part of the bulb and then the filament hanging out in there. Okay? So those two, either one is fine, resemble a light bulb or represent a light bulb. What else do you have?
Wires.
Wires, right? And wires naturally are kind of curvy. They're kind of funny. They do like woo, whatever like that. So if you're drawing literally what it looks like, they're going to look something like that. But that's not how they draw them in circuit diagrams. In fact, they draw them in a very not realistic way. They're just straight lines, first of all. And they're straight lines that bend at right angles. So they're not like little curves or anything like that. So it's going to be like, right? So that's like a wire that's bending, okay? And so I just want you to know that so that now you can take these three pieces and in just a moment, don't do it quite yet, I'll give you some time in just a minute, to translate your picture. I don't want you to erase your pretty picture, but I want you to translate your picture into an actual circuit diagram. Don't do it right this second. Put that pencil down. Because you're like, I want to do it right now. But I want to talk for just another minute so that we don't have to like pause a bunch of times. Is that okay? There's one thing that we haven't talked about yet that you're going to do in the second part. Has anybody looked ahead at the second part to find out what last little piece we're going to add into that circuit? Everybody can look in there. Look at part 2. What else are we going to add besides batteries and wires or something else? A resistor. So if you've never seen a resistor or played with a resistor before, they're kind of cute. They look like this, so that they've got wires coming out of them, and they're kind of like little tiny peanut, like in the shell shape. Okay, that's kind of what they look like to me, and then they've got little lines on them. So that is a resistor. We'll talk about what resistors do later, but for now, I just want to show you how to draw a resistor in a circuit diagram. So if I was going to draw the literal picture, it looks something like, I don't know, I'm not an artist, but something like this. Then it's got some lines on it, okay? But again, that's not what they want you to draw on a circuit diagram. It's going to be a line and it's just a jagged thing like that. There's not like a certain number of things it has to have, okay, but something to that effect. Is that okay? Okay. You look like you really want to draw a circuit diagram. I'm going to give you 45 seconds to draw a circuit diagram for the one you did in part 1, so you can do it, and then I'm going to bring you right back. Okay, so I'm timing you right now. Go. Kind of generally the answers to the other questions here. Most specifically, kind of about question number 2. Describe the path of an electron starting at the power source. What did you say for that? What did your group talk about? What did you come up with? What did you guys say, Allison? What did your group say?
The electron is the positive side.
Okay.
The batteries going through the wires and to the light bulb, or to the coil where the light bulb is attached, and then it goes through the metal part of the base of the light bulb into the filament.
Okay.
And then back out the other side.
Okay.
Back into the negative.
Okay. Does that kind of match with what people said? Yeah? How did you decide that it started at the positive end?
So we thought like when the electron was like done with its current, then it would come back to a negative end.
It just
kind of how we decided.
Okay, just kind of a partially arbitrary decision. Is that fair to say?
Yeah.
It's kind of like a reasoned arbitrary decision? Okay. Jordan?
We kind of thought that it would start at the negative end and then flow through everything to the positive end.
Okay. And so the description, all the middle stuff was the same as Allison's, but just the positive and negative you had switched?
Yeah.
Other inclinations, other ideas? What did you say? Anybody else? Positive to negative, negative to positive? Is there any way to test that, to know, based on what you, like, based on the equipment that you have with you right now? Can you think of any experiment that you could do to tell? It won't matter. It'll still be the same drop. I don't know of any experiment that I could do to tell exactly which way they go. Okay? And this is the funny thing, is that, like I said, in the way that the College Board did it, they gave us this thing. And usually when I teach circuits, I've already taught like 2.5 weeks or 3 weeks of electricity, okay? And we find out exactly why it's happening and what's going on. And so usually, quote unquote, when I teach this, the students know because we've already talked about all of it, but you guys are just being thrown into it. Like, how would you know? I don't know. We know it comes out one side, we know it goes in the other side, right? That's as much as we know. So let's talk about what this means for just a second so that I can kind of fill in the holes a little bit to help you understand what's going on. So I want to go back, because I always do, back to the frog, right? When in doubt, go back to the frog. I hold the frog up here, I let him go, what happens?
He falls back to you.
He falls, right? When I'm holding him up here, he's got some energy, would you agree?
Yeah.
Yeah, what kind of energy?
Gravitational potential.
Gravitational potential energy, right? When I let him go, that gravitational potential energy is converted into kinetic energy, and then he falls and hits the floor, and that's turned into heat, and blah, blah, blah. We've been through this 100 times, right? The same thing happens for electrons. Now, before I go there, I need to ask a question, because I made an assumption when I wrote this lab that we all knew that electrons were moving, and that it was the electrons that are moving. How do you know that it's the electrons that are moving? How do you know it's not the protons that are moving? I'm not going to call on you because everybody always waits for Jonathan to answer, so put your hand down. Sorry. No bad stuff. I just want to make sure that everybody's thinking. I want you to talk to your table mates. How do you know? Because you should, based on your science experience, you should know that it's electrons that move. How? Have a conversation right now, like a 15-second one. Go, go, go. Caleb, how do you know it's electrons that are going?
Protons and neutrons are in the nucleus, and now it's together.
The protons and neutrons are, where did you say?
In the nucleus?
In the nucleus. The nucleus, yes, the nucleus, right? Of the atom, does that make sense? Yes? Yeah. So you got the protons and neutrons in the nucleus of the atom, and you got the electrons where?
A shell and a
Right? Okay. Do all of the electrons move? Do all of the electrons that are in the wire flow? Huh? No. Let me ask this question. Do all materials conduct electricity well?
No.
No. The ones that do are called conductors. We know that. And you gave me examples of conductors a few days ago. We talked about that. What is it, chemists, that make conductors conductors? What is it that make insulators insulators when you're talking about electricity? What is it about materials that make them good conductors of electricity? Neither of you. I'm not going to talk to either one of you now. I'm so mean. Go.
The number of electrons in the outermost shell.
Yeah, what are those silly electrons called?
Valence electrons.
The valence ones, right? It's only the valence electrons that are going anywhere. The valence electrons are the ones that are really easy to move, right? That's the whole point of them. There are a whole bunch of electrons in copper, right? Copper has some number that's pretty darn high, which means it has a whole bunch of electrons, and it's not all of them that go, it's just the outside ones. The outside ones are going, okay? Doesn't make any sense that the nucleus or those innermost electrons are going anywhere. There's no reason for them to go anywhere, okay? But those outside electrons, they do go places. What would cause an electron to go someplace? What causes anything to go someplace? This is basic physics, friends. What causes something to go someplace? Make it even simpler. I mean, there's energy related, but if I have an object, I don't know, like a frog, and I hold it up here, and I let go of it, is it going to stay there?
No.
No, it's going to go someplace, right?
Yeah.
Where is it going to go? Down. Why?
Because of gravity.
Because it feels a force, right? Now, my next question for you is, in these wires that, you guys have this cute little circuit, and you broke it. Jeez. I told you to make the light bulb not light. I don't care. For my purposes, it doesn't really matter. Okay, so I have this this circuit that isn't lit up, and it's not lit up on purpose, okay? Right now, before I go like that, ding, 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 before I go like that, are the electrons moving? Please put your phone away. Are the electrons moving?
No.
Like
Not
in
yet.
their orbit.
Are the electrons moving? That's the question I asked.
Yes.
Yes. How do you know that they're moving?
That's what electrons do. Because the temperature is above absolute zero.
Because what?
The temperature is above absolute zero.
Right. If they weren't moving, that would mean nothing is wiggling, which means that they're really, really cold, right? Absolute zero. Is it absolute zero?
Yeah.
No, because we haven't made it absolute zero yet, and it's sure as heck not going to be with this circuit board that they do that, right? Like, that doesn't make any sense. Yeah, so the electrons are moving, but they're moving in just kind of a random motion. Does that make sense? Now, as soon as I go like this, now what happens?
That's it.
What happens to the electrons, River? They flow through the wire. So let's imagine we have all these electrons, right? And then this thing hits, and then they just start marching?
No. They start running. There you go.
No. They don't. They don't do that. The equivalent analogy that I make for this, if you put 300 seventh graders in the gym, okay, you just lock them in there. That's a good thing to do with seventh graders. I didn't say that out loud, but you know, you just stick a bunch of stuff, and what are they going to do? Are they just going to sit still?
No.
Of course not. Right? They're just going to be moving all around because it's not absolute zero in there. Right? They've got energy. And then you make an announcement. You say, free ice cream in the cafeteria. Okay? Most of them are probably going to be interested in that. Most of them are going to move towards the cafeteria. Would you agree? Especially if I unlock the doors. That would be really mean if I hadn't. If I unlock the doors and I let them, are they going to stand in straight lines and then start marching?
No.
Of course not. They're little seventh graders, right? They still bounce off of each other. They just bounce off of each other in a general motion, in a general direction, because they feel the force of free ice cream. You understand what I'm saying? It's the same thing with these electrons. So they're not moving in like a very, very orderly path, but they're feeling some general pull in some general direction. So they're bouncing around and somehow happen to get from one end of the battery to the other. So what does this battery do? Those seventh graders, or those electrons, are basically falling. They're feeling a force, right? They're falling from one side to the other. And then the battery chemically lifts them back up. Does that make sense? So they have some potential energy. Is it gravitational potential energy?
No.
No, you got a new name for it, right? Anybody want to give it a new name? Hey, that's a good choice. Yeah. So at the start, the electrons have electric potential energy, okay, that's provided, or I'm going to say, as a result of the connection with the battery. Okay? And once that battery is connected so that the circuit is complete, then those electrons fall. I put that in quotation marks because they're not literal, right? They're falling through a loop, okay? But they fall, and that electric potential energy, well, what happens to the gravitational potential energy for the frog? What's it converted to?
Kinetic potential.
Kinetic energy, right? But unlike the frog having all of this space, the electrons are more like those little seventh graders that are bouncing off of each other. So it's not turning into kinetic energy. They're not accelerating. Where is that electric potential energy going in this story? Where is that electric potential energy going in this story? Yeah, this is giving off energy, isn't it? Energy in the form of light and maybe a little bit of heat. So that electric potential energy, okay, the electron's going to fall, and that electric potential energy is going to be converted into heat. Oops. and light. Okay. Does that kind of make sense? We'll get into a little bit more of it later, but the thing that I want you to know is that most of the energy is going to be converted inside the filament. That tiny wire is designed such that most of the energy will leave there, okay? Just a little tiny fraction of the energy is actually dissipated in the wire itself. So most of it comes from, or goes into heat and light. Okay, so the wires are almost perfect. They're just not quite. Does that make sense?
Yeah.
Okay. Okay. It was a lot of me talking. I apologize for that. I know that's kind of a lot of things, but I wanted to make sure that makes sense. I'm going to let you keep working for another few minutes, and then I will interrupt you again to show you the meters before the end of the block today. Okay? So finish up goal 1, and probably in about 4 or 5 minutes I'll regroup you again.
Let's try it.